Okay, so I'm going to want you to really have a handle on these ideas of this comparison theorem. So, and these were just ideas that I just was trying to exercise your brain in those previous examples. Okay, so if I have f and g continuous functions, and I know that f of x is larger than g of x. So let's get a picture going here. So here's f of x, and I'm talking about a to infinity. So there's f of x, and let's just put g of x below it, right? G of x. Okay. So this is the relationship. I know f is larger than g. Okay. If I know that the area under f of x from a to infinity converges, if I know that this area adds up, the blue area adds up, that's what it means it converges, right? That this would have a limit. Then I know it's a given because I have this relationship between these two, and I did forget to say these have to be positive. That the area of the black, right? I'm trying to get black here. Black of the black g of x that's below it, won't it be convergent as well? Yes. So if the bigger converges, that means the smaller will converge. So the bigger converging is good. So the larger having a converging is a good thing. All right, so let's do this again. So let's keep g of x black. So here's g of x, and if I know from a to infinity, oops, sorry, typo, a to infinity, if I know that this adds up to infinity. Okay, so this is infinity, a to infinity of g of x, right, adds up to infinity, and I'm keeping the same relationship. So what do I know? That f is larger than g. So f is still up here, right? F is larger than g. So what do I know about the area under the blue if I know that the area of the black is infinity? Well, the area of the blue must be infinity as well. So the smaller diverging is good. Okay, so this comparison test or comparison theorem, when we're in integrals with these improper integrals, you'll be asked to use the comparison theorem. So remember only to use it when the instructions say use comparison theorem, because I still want to see you do the integral on many of them. Okay, so why do I have that here again? Oh, only be using comparison test on improper integrals. I'm just reminding you of what improper integrals are, right? So improper integrals type 1 are horizontal asymptotes. Improper integrals type 2 are vertical asymptotes, correct? So that's what improper integral means. So one of these two types where you'll see infinities or where you have a vertical asymptote somewhere. Okay, here we go. So this is a typical question where it'll say use the comparison theorem to find out if it's convergent or divergent for this. Okay, so this is an impossible integral to do. There's no infinity. So that tells me that there must be a vertical asymptote somewhere. Ah, I see it. The vertical asymptote occurs at x equals 0. Okay, so in order to use the comparison theorem, I need to build an inequality. This takes you back to good old squeeze theorem days, right? Only we're not squeezing anything, we're just having one inequality. So I'm going to start with the true fact that I know, and I know that sine squared is smaller than 1. Then I'm going to build this function that's inside the integral. So I'm going to take this and divide both sides by root x. Okay, so I've got the first of the criteria established where I've got the function I'm trying to show is convergent or divergent is one of them, and now I've got this new function. This new function I can take the antiderivative of. So I pick up the limits of integration from the first problem of my new function. I know I have a vertical asymptote, so I have to write it as a limit. As t goes to 0 from the negative side, right? If I'm going from 0 to pi, I'm coming in from going to 0 to pi, I'm going from the positive side. Sorry about that, positive side. Then I'm going to rewrite this. Positive side, positive side. Okay, so I'm going to rewrite this as a limit. T goes to 0. Put the T where the 0 was. And if you needed to, you could take the time, right? Take as many steps as you need. So T to pi, x to the negative 1/2 dx. Add 1 to the exponent, so x to the 1/2 over 1/2 or times 2. Plug in the pi, subtract off plugging in the t. Now plug in 0. If I plug in 0, that goes away, so I'm left with 2 root pi. Okay, so what do I have? I have that fact 2, which I'm talking about, is I know that now 0 to pi of 1 over root x dx converges to 2 root pi. So that means this converges. So I have two facts. I've got these two compared, right? Whoops, let me underline here. These two compared. I have that the larger one converges. The larger converges means the smaller converges by the comparison theorem. So there's the two facts you have to establish. The inequality between the two functions. You have to show the work of whether the new function integral converges or diverges. This does the right thing. It converges. So that must mean the smaller converges also. So you just need to rewrite what the original integral was and just say it converges by comparison theorem.